Okay, today we have derivatives of natural, exponential, and logarithmic functions, e to the x, ln of x, okay, to the normal people. It's really quite simple. A lot of your e to the x's are going to have chain rule implications. What I mean is you're going to be using the chain rule along with it. We're also going to learn how to take the derivative of functions on a calculator, and this means that we will be starting our calculator and non-calculator sections. So let's get right to it. Not a hard lesson today. Differentiation rule for natural exponential functions. So let's once again start getting used to this notation. This means the derivative of respect to x of e to the x is equal to e to the x. Now if I have a composite function with something other than x here, then of course I have to use the chain rule. So, a couple of quick easy examples. E to the sine x. Oh, well, we have something up here. So the derivative of e to the x is e to the x. The derivative of e to the anything is e to that anything. So here is f prime of e to the sine x times, because of the chain rule, the derivative of the inside of this function, which is the exponent. So the derivative of sine is cosine. There you have it. Same rules here. Let's get focused here. So e to the 2x plus 3 is going to be e to the 2x plus 3 times the derivative of 2x plus 3. So e to the x, the derivative of e to the anything is that anything. So e to the 2x plus 3 times 2. So clean it up, 2e to the 2x plus 3. Fairly simple. Alright, even easier, 3e to the 2x will be 3e to the 2x times the derivative of 2x, which is 2, leaving you with 6e to the 2x. This is e, this is chain rule, this is everything. Alright, here it looks like we're going to have chain rule and product rule. So you've got your two parts here. You've got your first part and second part, as I call it, f of x, g of x. So it's the derivative of the first part, which is 2, times the second part, e to the 3x, plus, let me mark my notation down so we don't get confused of what we're doing here. Now, the derivative of e to the 3x is e to the 3x times the derivative of 3x, which is 3, times the first part. Not much really we can do here. We can clean this up a little bit, giving you 2e to the 3x plus, this gives me 3e to the 3x times 2x plus 3. So you're going to have a like term right here. I wouldn't count off on it, but I hate to leave two of the same term anywhere. I know you do too. 6x e to the 3x plus 9e to the 3x. Now I've got 11e e to the 3x plus 6x e to the 3x. Okay? Come on, camera, focus up. There it is. All right. Moving on. All right. So here we got chain rule times 2. I'm looking at the bottom right one, by the way. All right, we've got e to the 2x plus 6 times inside of a square root. So, a couple ways you can handle this. Well, I've got a power to a power right there, and you could multiply that all through and get x minus 3. Or you could use the chain rule times 2. I'll do it both ways, because this little shortcut does not always work. Times 1, which would be the derivative of the inside, so it's just e to the x minus 3. Let's see if we get the same answer. So this is e to the 2x minus 6 to the 1/2 power. So I got 1/2 e to the 2x minus 6 to the negative 1/2. Alright, that's the first part. Then I take the derivative of the inside, which is e to the 2x minus 6. Then I take the derivative of this part, which is 2. 2's cancel. That's good. Now, these are the same terms multiplied together. This is to the first power, so what I do when I multiply the same base to the power, I add the powers. E to the 2x minus 6 to the 1/2. Distributing here, or you could leave it as the square root. They don't look like the same, but they sure are. E to the x minus 3. Okay, so chain rule, chain rule. The last one. We've got chain rule and product rule. Derivative of the first part equals 2x times the second part plus the derivative of the second part, e to the 2x, times the inside, which is 2, times x squared. So I'm left with 2x e to the 2x plus 2x squared e to the 2x. And no, you cannot combine those. All right. Next problem. E to the 5x over 3x squared. So this is a quotient rule. So we take the derivative of the top part. Derivative of e to the 5x is e to the 5x times the derivative of the inside, which is 5, because that is the chain rule. Gotta have a good base of knowledge of the chain rule, or you're going to struggle on all of these concepts. Now the derivative of the bottom is 6x times e to the 5x. All of this multiplies out 15x squared, 15 x squared e to the 5x minus 6x e to the 5x all of that over 9x to the 4th. If I wanted to simplify this, I could divide everything through by 3 and x and get 5x e to the 5x minus, excuse me, not 6, minus minus 2 e to the 5x, all of that over 3x cubed. Alright, so fairly straightforward. If you know all your rules, the e to the x shouldn't throw you off much. Alright. Well, almost just as easy is the derivative of the natural log function, ln of x. Derivative of ln of x is 1 over x. Of course, what do you think you see here? Chain rule, chain rule, chain rule, chain rule. That's the only way I can make this any kind of difficult. Okay? So, derivative of ln of 2x minus 3, just like e to the x, you go ahead and just go 1 over 2x minus 3. Now, this isn't a simple x, this is 2x minus 3. So because of the chain rule, we go in and multiply it by the derivative of the inside, which is 2. So I get 2 over 2x minus 3. All right, let's get focused, people. Camera. The derivative of this is 1 over 3x squared plus 2x times the derivative of this, which is 6x plus 2. 6x plus 2 over 3x squared plus 2x. Here we've got chain rule times 2. So I've got 1 over square root 2x minus 4 times the derivative of 2x minus 4, the square root of 2x minus 4. Now if you recall, the square root of 2x minus 4 is 2x minus 4 to the 1/2. 1/2 2x minus 4 to the negative 1/2 times 2. So you have to use the chain rule here as well. So I get 1/2 2x minus 4 1/2 times 2. I'm running out of room. What happens? Alright, so let's just get our bearings about us here since I ran out of room. I'm going to take this 2 that you can't even hardly tell and put it on top. Don't be confused about where it came from, okay? It came from the derivative of the square root of 2x minus 4. You bring your 1/2 there, you subtract 1/2, and then you take the derivative of this inside, which gives me 2. So when I did the derivative of ln of all of this, it's 1 over all of this times the derivative of it. And here it is. Okay? So I just plugged it in. Don't get confused because my sloppy work. 2's immediately cancel. This is the square root of 2x minus 4. This is the square root of 2x minus 4. The square root of x times the square root of x equals x. The square root of a times the square root of a equals a. The square root of 2x minus 4 times the square root of 2x minus 4 is 2x minus 4. Alright, so feel free to rewind this if I lost you in the process of that, because I know I got messy. Alright, ln of cosine x. Well, 1 over cosine x times the derivative of cosine x is minus sine x. Uh-oh. Trig identities. Minus cosine x, or excuse me, minus sine x over cosine x equals negative tan x. All right, moving right along. So, a good way to check your work in your homework: do not become dependent on your graphing calculator. But here is finding derivatives with the graphing calculator. So, what's it want us to do? Find f prime at the indicated value of x, then determine increasing, decreasing, horizontal tangent, or vertical tangent. Alright, so if it's increasing, we know our derivative will be greater than 0. Our derivative will be less than 0 at decreasing. Our derivative will be equal to 0 at horizontal tangent, and for a vertical tangent we're going to get undefined. So our calculator will give us error. So that's all we're doing. So how do you do this on a graphing calculator? Okay, first you hit on, then I hit the math button. And you can scroll down, it's number 8. So I hit math 8. Now this, remember what this notation was. The derivative with respects to what variable? Well, the only thing you know right now is with respects to x. So here we'll plug in our function, 3 e to the x times sine x, and we want to know when x, or it says a in this particular example, equals negative 2. And I get negative 0.538. Your AP Calculus test, I found out in my fun training, wants 3 decimal places for every answer. So 3, 8, make sure we can round. What does that mean? Is it increasing, decreasing, horizontal or vertical tangent? It's negative, therefore it is decreasing. So it's actually going to take you more time to type these functions in than it is to find your answer. Same exact function. Learn this graphing calculator stuff, okay? Look at this blue word right here, entry. So how do you get to the blue buttons? If I hit second. If I hit second, enter, it's going to pull up exactly what I entered in last time. All I have to do for this particular problem is change my x value from negative 2 to 1. I get 11.268, which means it is also, or excuse me, not also, this one is increasing. Alright, new function. So remember, math 8, derivative with respects to x of ln. I'm going to go ahead and put in parentheses ln of cosine x so it doesn't get it confused. I don't know if that helps. It always makes me feel better to put in more parentheses than I need. So I'm going to close out the parentheses with the x with the cosine x and with the ln x, and I divide that by x, and then we want to x approaches, oh sorry, this is x squared, so second insert, square it, and this is as x approaches pi divided by 3. Negative 3.351. Negative 3.351. And that also means that we are decreasing. Same function. Pull up the same thing you just typed in. Second, enter. This time I'm going for pi. Non-real answer. What do you think that means? This means undefined. We are looking at slopes, and when our slope is undefined, that means it is a vertical line. So here we have a vertical tangent. Next problem. New function. So we'll go math 8, derivatives with respect to x of e tangent of 0.34x as x approaches 0. Well, you know this. Tangent of 0 is 0 over 1 is 0. E to the 0 is 1. So this one equals to 0.340000. Number 6. X is approaches x. Oh, I'm sorry, we didn't finish this one. This means it is increasing. Plug it into the calculator. 5. All right, now sine squared. Remember what this means. This means sine of ln of x squared. And that's as x approaches 1. Alright, so scientific notation, people. I'm going to tell Miss Owens if you don't get it right. If I move this 0 over 6 times, then that is going to be very, 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 very close to 0. The calculator is not smart enough to realize that the derivative of this is 0. Therefore, it has a horizontal tangent. Okay, that's using your graphing calculator. Same thing. These are what we call some application problems here. Alright, so when the value of the derivative of a function is positive increase. The function is increasing. When the value of the derivative is negative, we say it's decreasing. When speaking of quantities, increasing, decreasing, we do so at a certain rate. So as I turn on, all right, so imagine me poking a hole in a bucket. All right, the amount of water is the original function. The rate at which the water falls out okay, this is the rate, the amount and rate. What's going to happen as this water starts to get towards the bottom? It's going to go slower and slower. So that changes based on the amount of water in there. So when speaking of quantities increasing and decreasing, they do so at a certain rate. We already understand the derivative to be the slope of a tangent line. Slope is rate. Therefore, the derivative function actually represents the rate at which the function is changing. Huge, huge concept. Okay, right? Because if I'm driving down the road, here's time. Okay, here's rate. If I'm driving down the road and I floor it, see how this horizontal tangent has gone up? My rate is increasing. Okay, so rate at which is changing is derivatives. So number of people entering a concert can be modeled by this equation: f of t 560 e sine to the t, where t represents the number of hours the gates open. Okay, find the values of f of 1/2. So f of 1/2. Okay, f of 1/2. All right, this function f models the number of people attending a concert. So f of 1/2 means, all right, remember t is the amount of people after t hours. So when t is 1/2, that's a half hour. So this equals the number of people at the concert after t hours, or in this case, half an hour. So you just plug it in. So we go 560 e to the sine 1/2. Well, plug it in your calculator. 560 e sine 0.5. So this means that they're after, so 904. So this means that after half an hour, there are 904 people at the concert. F prime of 1/2 means it's a rate. What rate is it? If you're going into a concert, the rate. All right, so maybe at the beginning of the concert when Ellie just made me laugh. When the people are piled up, it's coming in at a faster rate. But towards the end, people, as the concert's going, people aren't coming in as fast. So f prime of 1/2 is the rate at which the people are coming in. At time t. Okay, so we have to take the derivative. Use your calculator at time t, which is 1/2. So math 8 x 560 e to the sine of x, which in this case 1.5 and 793 people per hour after 30 minutes. All right, so how many people have entered the concert after 2 hours? So we're looking for a number of people, not a rate, number. So for the number of people, we're going to look for f of 2 at time 2. So 560 e to the sine t, which is 2, and that is going to be, let's use our calculator just for fun. Isn't this fun? So I don't want to use the very last function I pulled up. I want to use the one before. So you hit second enter, and just change the 0.5 to 2. Wow, that Coach Henderson is some kind of smart. And that equals to 1,390 people, roughly. All right, so is the number of people increasing or decreasing? So after 2 hours, you've been to a concert. After 2 hours, don't people typically start leaving? I do. I can't stand there and listen to the same guy sing for that long. So we're looking at is the number of people entering, the rate at which people are entering, increasing or decreasing. Is the rate positive or negative? So f prime of 2 equals, once again, we don't want the very last function, we want the one before it, so we go second. Oh, come on, computer, calculator, focus. Enter. There it is. Second enter. And we're changing it to 2 hours. And it's a negative rate, so negative 570 people per hour. So it is the number of people is decreasing. People are leaving. Good application problem. We'll see these again. After being poured in a cup, coffee cools at a temperature T of T, where big T is the temperature and little t is the time in minutes. So there's your equation we're modeling. So if I want the temperature, I plug it in there. If I want the rate at which the temperature is cooling, I find the derivative and plug it in there. So the first question, what is the temperature? Not a rate. Not a rate. Don't mess with the derivative. So we just plug 5 into there because this is t in minutes. So I'm going to use my calculator because this is a calculator test or portion. So 70 plus 110 e to the negative 5 divided by 2. That equals 79.029 degrees. Now, is the temperature decreasing faster? So faster, slower, rate. Is it decreasing faster or slower in 1 minute? So remember, at 0, it's neither increasing or decreasing. So the further I get away from 0, the greater absolute value, the faster it is happening. So we're going to go t prime of 1, t prime of 3, and compare these answers. So go math, 8, x, and this is 70 plus 110, second e to the negative 5 halves. And we are going from 1 for the first one oh, I'm sorry, I put 5 over 2 in again. I get negative 33.359. And then we plug in, we want to know how fast it's decreasing. So it's decreasing by a rate of 33 degrees per minute after 1 minute. Well, just think about that. After 3 minutes, if it keeps decreasing, it's going to be negative degrees for long. Didn't say we put it in the refrigerator, it just said we left it out. So obviously this rate is bound to slow down. But just for fun, let's plug in 3 minutes. And just what we thought, the rate is not as steep. 12.272. So it is, the temperature is decreasing faster after 1 minute. Okay, so this is kind of the first time you've seen temperature, or excuse me, derivatives as a rate. So, real important concept. All right, so along with this goes homework 21, I think. I don't know. Do it anyway.